As mentioned, for the remainder of Unit 2, we're going to concentrate specifically on linear functions, the ones that just have x to the first power. In the last section, we kind of generally said a linear function would look like this. F of x equals ax plus b. Notice we've got our x to the first power, making it linear, and then possibly a constant term. When we're talking about linear functions, it's actually very common to use the letter m here rather than a, but we'll talk a little bit more about that as we go along. All right, so I want to start talking about different representations of linear functions: analytic, numerical, and graphical. We'll be doing that every time we start talking about a new function family. So in example 1, I have a specific analytic linear function. F of x equals 3x minus 5. We're going to create the numerical table of values, and we're also going to create the graph. And at least for this first one, I'd like to do it by hand. I feel like just getting yourself kind of into the problem and thinking it through by hand the first time kind of helps us to understand. So let's do that. If I want to go ahead and plug in each of these x values, I'm going to say, first of all, when I plug in -2, I would have 3 times -2, subtract 5, -6 minus 5 would be -11. We'll keep on going, plugging in x equals -1, -3 minus 5 is -8. When x is 0, 0 minus 5 is -5. When x is 1, 3 minus 5 is -2. When x is 2, 3 times 2 is 6, minus 5 is 1. Plugging in x equals 3 is going to make that 9 minus 5, or 4. And plugging in x equals 4, 12 minus 5 would be 7. Just a little bit of arithmetic there. All right, before I actually draw the graph, I'd like to look at the question right down here. Look at the pattern established by the y values in the table that we just made. Do you notice anything? First of all, I'm going to point out to you that I was very deliberate in making sure that these x values went up by 1 each time. Is there a pattern in the y values? Well, if you'll notice, the y values increase by 3 each time, right? 1 plus 3 is 4, 4 plus 3 is 7. That pattern works all the way through the table. It's actually not a coincidence that that 3 is also the multiplier of x in our linear function. Again, more on that later. But what we're noticing is that in our linear function, when x increases by 1, y changes by a constant amount. As we look at more tables of values for linear functions, we'll see that same pattern over and over again. In a linear function, if the x values go up by 1, the y values will change by the same amount every single time. All right, let's take a couple of minutes and graph these points. Let's see, -2, 11 was my first one. I didn't quite have enough space, so I'm going to start with -1, 8. And so on. You take a minute or two and do the same. I'm so sorry. I'm starting positive rather than negative. Goodness. Let me fix that. -1, -8 down here. 0, -5, and so on. And so I've got some individual points plotted. Of course, I didn't choose to put fractions or decimals into my equation, but I certainly could have. This is a continuous function. And you'll notice that if I connect the points that I drew, I do indeed get a straight line. And not surprisingly, that's really where the name linear comes from. The graph of a linear function is a straight line. Now remember what we saw in the table. We saw that when x went up by 1, the y values increased by 3. Can we see that same pattern over here in the graph? Well, in fact, we can. Pick any point. I'm going to start here at the y-intercept, -5. If x goes up by 1, so if I move over 1 unit in the x direction, what happens to y? Well, if x goes up by 1, y goes up by 1, 2, 3. And I see that over and over again. X goes up by 1, y goes up by 3. And you can see it all the way through this graph. That fact is actually what creates that linear shape, that constant rate of change. So in the graph, when x increases by 1, we see y increase, in this case, by 3. I probably should have said here y changes by the constant amount 3 in this case. What about in the equation? Well, as I mentioned earlier, in the equation, the 3 was the multiplier on the x. So we're seeing that 3 tells us a lot, right? It tells us how much y is going to increase by when x goes up by 1, both in the table, but also when we think about the graph. In the graph, sometimes we have a specific name for kind of this sort of pattern that we're seeing in a linear function. We say that the 3 here is what we call the rise, how far up we go, and the 1 is called the run, how far over we go. And so I've got 3, up 3 when I go over 1, and that corresponds to 3 in the equation. We're going to come back to that a little bit later on and talk about it a little bit more generally. But for right now, I just again want you to see the correlation, the relationship between the table, the graph, and the equation. So what we just noticed is probably one of the very most important features of a linear function, specifically that a linear function always has a constant rate of change. It's that increase by the same amount in the y column of the table. It's that constant increase that gives the shape of a line on the graph. Formally, we call this the absolute rate of change. And we say the absolute rate of change is constant in a linear function. This whole idea of absolute rate of change we'll see by contrast a little bit later in the course. But for right now, we'll typically just say rate of change, but no, it's really what's called an absolute rate of change. All right, on the graph, the constant rate of change is visible as that steepness of the graph, how far it rises or possibly falls. And we give this a name. We call it the slope of the line. Traditionally, we actually use the letter M rather than A to represent the slope. So usually our linear function actually gets written as f of x equals mx plus b. or sometimes just y equals mx plus b, where this m represents what we call the slope or steepness of our line. So for the linear function, f of x equals mx plus b, what we just saw, every time x increases by 1, y is going to change by whatever the value of that m, that slope, is. And again, m is called the slope of the line. All right, so now that we've kind of investigated what m is, it's the constant rate of change, let's talk a little bit more about the b. If we start with our function, f of x equals mx plus b, what happens if I ask us to find f of 0? Plug the 0 in for the x, right? And so that's just going to be 0 plus b, or b. So when x is 0, y is b. Well, let's see, if x is 0, that's the point on the y-axis, or in other words, the y-intercept. So for that linear function, f of x equals mx plus b, when x is 0, the value of y is b, and that gives us the y-intercept of the line. So the two constants in our function, m and b, are very significant. M gives us the slope, or constant rate of change. B gives us the y-intercept of our line. Because of that, this form of the equation, y equals mx plus b, is usually called the slope-intercept form of the equation of the line. And it gives us so much great information that typically if we get an equation in a different form, we'll typically rearrange it to that form so that we can use all of this information that we've just developed. All right, so I'm going to capitalize a little bit on what m and b represent. And we're going to see if we can find the equations of a few lines. The first two are given to us in numerical form, tables of values. And we want to find an actual equation. We want to find the analytic form for the linear function. So first of all, I'm going to notice with an input of t and an output of h, my equation is going to be h of t. Now the next thing I need to know is the slope. So I'm going to verify to myself the inputs do go up by 1. And then I'm going to ask myself, what's the pattern in the outputs? And it looks to me like it's subtracting 5 every time. So that means my slope, my m, is negative 5. So down here in my equation, I'd have negative 5, not x this time, but t for my input variable. Now the b is the y-intercept. And I've got that right here. When the input is 0, the output is 15. So that right there tells me b is 15. So to finish my equation, I'll put the plus 15. Usually we think mx plus b. In this case, it happens to be mt plus b. But there's the equation of my line. All right, what about over here? If you want to take a moment and try this one on your own, you might want to pause right now. I'm going to go ahead and get it started. So first of all, I'm going to notice input n, output a. So my function is a of n. And then I need to use my table to hopefully figure out M and B. So first of all, I verify the inputs do go up by 1. And then I take a look at my outputs. And let's see, the pattern is maybe most obvious right here. Looks like I'm adding 0.7. Does that work all the way through? Plus 0.7, plus 0.7, plus 0.7. It does indeed look like we are adding 0.7 each time. So 0.7 is our constant rate of change, or our slope. So I could start right away and say A of n would be 0.7 times n. And then I need the B value. Last time I was really lucky because the B value was right there. And so all I need to do is grab it right out of the table. This time there are a couple of different options, but for right now I'm going to work with the pattern. I'm going to see if I could actually predict what would happen when the input is 0 by kind of working my way backwards on the table. Let's see, if I was going in order, I would go back to 1 and then finally back to 0. And if my numbers this way are going up by 0.7, then to go backwards on the table, I'd actually have to subtract 0.7. Okay? So I would have to say 2.6 minus 0.7 should be 1.9. And then 1.9 minus 0.7 should be 1.2. So because they didn't give me the y-intercept, the b value, I just used the pattern established by the slope to figure it out for myself. Now that I've got that, I can see that b must be 1.2. So there we go. M times my variable, my input variable, n plus b. All right, I still want to find the analytic or equation form, but in C and D, I start with the graph instead. So once again, let's see, it looks like this one doesn't have any extra variables labeled, so I'm going to assume then that they're x and y. That's the default if they don't give me anything else. And so I'm looking for y equals mx plus b. And the first thing I'm going to try to do is figure out the slope from the graph. Now remember, when x goes up by 1, y goes up by the slope. So I'm thinking, let's see, if I start over here, let's see, that would be -1, 0, +1, and so on. If my x goes up by 1, what does my y go up by? Well, I may have to try to estimate here. This goes from 0 to 100, so I'm thinking this looks like it's probably 50. That means that right there is probably 25. I think that makes sense, because if that's 25, and I go over one more and up, that would also go up by 25. Right, so the pattern kind of makes sense. Over 1 up 25, over 1 up 25, over 1 up 25, and so on. So I think my slope is 25. So I'm going to start with y equals 25x. And then the y-intercept right here is 50. So b is going to be 50. All right, we've got one more graph again. I would encourage you to pause for a moment and try it on your own. This one I'm going to notice that my input is t and my output is m. So I could write this one in function notation as m of t. By the way, I didn't write this one in function notation. I could have if I wanted to, right? I could have written y of x equals 25x plus 50, or I could have made y equal to f of x, or whatever letters I chose to use. But this one, they gave me the variables. The input's t, the output's m. All right, so I need to start with the slope. When x goes up by 1, what happens to y? So I'm actually going to start, let's just go ahead and start right here on the y-intercept. We already know that's the y-intercept, so b is 6. When I get to the point that I need that, I already know it. Now it looks like if I let x get bigger by 1, it looks like the y value just goes down by 1, negative 1. Let x go up by 1, y goes down by 1. And you can see that that pattern repeats itself over and over. So it looks like the slope is going to be negative 1. So m of t would be negative 1 times t plus 6. Or if I want to, I don't really need the 1. We often just call that minus t plus 6. So, moral of the story, you can go between the numerical table of values, the graph, and the equation, as long as you remember the slope is the rate of change. It's what happens to y when x goes up by 1. And the b value is simply the y-intercept, what happens when x is 0. All right, let's put that in context for an example or two. So we're always going to look at some applications when we learn stuff. So in example 3, the value of many things depreciates or goes down over time. For example, suppose a business purchases a copy machine for $22,500. The value of that machine will decline with time as the machine ages. Typically, companies in particular track that kind of thing because they can write it off on their taxes. This table is showing us the value of the machine t years after it was purchased. So after 1 year, it's gone from its original value down to $21,000. And after 2 years, it's at $19,500, and so on. So first of all, if I want to write a function, v equals v of t, how do I know this function should be linear? Well, the table tells me it's linear because of that constant rate of change, right? When the inputs, the t values, go up by 1, what happens to the value of v? Looks like we're subtracting $1,500 every time. So when t goes up by 1, v decreases by the constant value of 1,500. Okay. That constant rate of change. That's what tells me it's linear. All right, if I'd like to find an algebraic formula, an analytic formula for v of t, I already have the first thing that I need. I already know the slope, the m, right, is negative 1,500. Now I don't have 0 in my table, but actually they told it to me and it would be easy to figure out in any case. We purchased the machine for $22,500. So at time 0 years, when it's brand new and no time has passed, it was worth $22,500. Or alternatively, notice I could have predicted by simply adding the 1,500 back in. So my B value is 22,500. All right, so I've got my analytic formula. The next question, what's the slope and what does it represent? The slope, the m, is negative 1,500. And we're kind of restating what we already knew. And we kind of already said it in part A. It stands for the fact that the value of the machine decreases by $1,500 per year. We'll do a lot of interpreting slopes in this unit. And in general, when you interpret a slope, you're always going to interpret it as how the output or dependent variable changes. So the output, the value, in this case decreases because it's negative by this much, the $1,500. And it's always per whatever the input variable was. Sometimes it's years, a lot of times it's years, but not always. All right, what is the V-intercept and what does it represent? Now, when we think about intercepts, I'm going to talk a little bit more formally about those algebraically. This one you probably could just read off what we've already done, but I want to talk algebraically about what that actually means from the formula. When we're finding an intercept, graphically, we look at where it hits that axis. But when we think about it from a formula perspective, from an analytic perspective, what we really are saying is what happens when the opposite variable is equal to 0. So for the V-intercept, I'd be looking at what happens when t equals 0. Well, if I grab my function right here, and I plug in 0 for t, of course 0 plus 22,500 is 22,500. So the V-intercept is 0, 22,500. And it means that when the machine is new, it was worth $22,500. All right, what about the other intercept? What if I want the t-intercept? Again, if you say, hey, graphically, it's where we cross the t-axis. But in terms of the formula, that means I have to put the opposite variable, in this case the v, equal to 0. So that means 0 is going to go on this whole side. And if I want to solve that little equation, I'm going to add the 1,500t to move it to the left-hand side. And then I'm going to divide both sides by the 1,500. And I get 15. So let's see. The t-intercept is actually 15, 0. And what that means is that after 15 years, the value is 0. Just a little bit more about that t-intercept. That t value, that 15, has another name. It's also called the zero of the function v of t. And the reason for that is it literally makes the function equal 0. So we say 15 is the zero of our function v of t, because v of 15 makes the function 0. We'll talk about zeros a lot this semester, so it's a good vocabulary to start introducing. All right, we have a couple more questions about this particular problem. I'm going to continue to work by hand for now. Just remind us what v of t looked like. The next question was, what is the value of the machine after 9 years? So we're saying t is 9. So I'm going to find what is the value v of 9. And that just means plugging the 9 in for the t. I'm getting $9,000. And then one last question. When will the value of the machine be $4,250? So that's the value. I want to put that $4,250 in for V. All right, and to solve this by hand, I'm going to subtract the 22,500. Gives me negative 18,250 equals negative 1,500t. And then we'll divide both sides by the negative 1,500. So about 12.17. And that would be in years, a little bit more than 12 years for the value to be reduced to 4,250. All right, we have one last example in this section. Example 4 here. In the year 2010, 40.9 million Americans traveled for Thanksgiving. The number of Thanksgiving travelers has increased by an average of 1.6 million per year. Source given there. And the first question, how do you know the situation could be represented by a linear function? Well, remember in the last problem, we actually had a table of values, and so we could see that constant rate of change in the table of values. This time we don't have a table of values to look at, but in fact, they actually tell me what the constant rate of change is right in the problem. You see it? It's right here. The number of travelers increases, on average, by 1.6 million per year. When they tell me the constant rate of change, that tells me I should be using a linear function to model the situation. So there is a constant rate of change. that increase of 1.6 million per year. All right, next it says to define the variables, and then we'll write an equation for our function. So let's see here. We're talking about change over time, over years again. So I'm going to use t for time to represent years. And I always like to have a starting year, right? I don't want to just use the actual value of the years. The numbers are just too big. So in this case, they did give me a good idea. They told me what happened in the year 2010. So I think it might be a good idea to use 2010 as my starting year and define t as the years after 2010. Let's see. The number of travelers, I'm going to call that n. We'll call that the number of travelers. And it is going to be in millions. So my function is going to look like n of t. All right. The slope is the constant rate of change. That's the 1.6. So I have 1.6t. Plus, what happens when t is 0? Well, when t is 0 in 2010, we knew there were 40.9 million travelers. So that means my b value is that 40.9. That's actually a big advantage of having set my t as years after 2010. It meant I knew what happened in the t equals 0 year. And that meant I really knew my b value right away. Very helpful. Right. Next question, use our function to estimate the number of Thanksgiving travelers in 2017. So let's see, I want to estimate n, and 2017, that would be 7 years after 2010. So I'm going to plug in t equals 7. And I'm getting 52.1. And remember, that was in millions. All right. In part D, a reporter was asked to write an article about how COVID-19 changed people's travel habits. In 2020, 50.6 million Americans traveled for Thanksgiving. Use the information in this problem to draw a conclusion that could be included in this article. What are the kinds of questions or what might be interesting here? We know how many Americans actually traveled, and we also kind of knew what the pattern had been. It might be interesting to say, hey, is this the number I would have expected? Or did people actually stay home and did fewer of them travel than would have been expected in that year? So that's what I'm going to try and do. So I'm going to say, well, let's see. How many, based on our function, would we expect in 2020? Well, 2020 is 10 years after 2010, so I want to plug in t equals 10. So 1.6 times 10 plus 40.9 is 56.9. And of course that's in millions again. Clearly we would have expected, based on our pattern, our function, we would have expected quite a few more people to travel than actually did. So if this reporter is writing the article, they could certainly first of all say, yes, Certainly a significant number of people seem to have chosen to stay home in 2020 rather than travel. And in fact, they can even conclude that we're about 6 million less than would have been expected. So if I take the 56.9 expected and subtract the 50.6 actual, the difference would be 6.3 million. And we can say about 6.3 million fewer travelers than, I don't want to say normal, I think I'll say expected. Sometimes when you see articles written where they say, oh, because this happened, such and such was this much more or this much less, you might wonder, well, how do you know what it would have been if this hadn't happened? Typically, it's because they're using modeling equations like this to make a prediction about what would have been expected and then comparing what actually happened to that number. All right, that brings us to the end of 2.2.